We started this section by looking at various normal distributions that had means and standard deviations that were not 0 and 1. So how do we handle other distributions with a different mean and a different standard deviation? We only have this one table. So we only have a standard normal table. Now, when we go to StatCrunch, it doesn't actually matter. We don't have to use the standard normal table. But before things like StatCrunch were a thing, then we needed to do what's called standardization. Basically, we're going to find what's essentially a z-score for our interval. So look on the left. If we're trying to find the probability that any x value is between a and b, where you have a normal distribution centered around some mean mu, we can actually get an equal area by standardizing it to have a mean of 0 and a standard deviation of 1, and you get these new a star and b star values. So we can do any normal distribution using table 2, but first we have to get the standard values, which is as simple as taking your original value and subtracting the mean that's given to you for the normal distribution and dividing by the standard deviation. So we have an example here looking at some information about full-term baby weights. So here the data suggests that you can describe the weights of full-term babies born in Canada with a mean of 3,500 grams and a standard deviation of 550 grams. So what proportion of baby weights in Canada are between 2,900 and 4,700 grams? What this is asking numerically is being between these two numbers. Now notice I am using an x here and not a z because z specifically comes from a standard normal distribution, and this distribution is not standard. It's a different mean and standard deviation. So in order to do this problem, we need to turn it into z values. So you take that 2,900, you subtract the mean, and then you divide by the standard deviation. It's very important that you subtract first. So 2,900 minus 3,500, and then hit enter, and then divide by 550. If you don't, you will get the wrong answer. The calculator needs to group the numerator values together and the denominator by itself. So make sure you either use parentheses around that numerator or you do it in 2 steps. So here we get negative 1.09, and 2 decimal places is plenty because that's all you have on the table. So negative 1.09 corresponds to 2,900, and we'll do this again for 4,700. If you get answers here when you're doing this conversion that are not between -4 and 4, that's a key that you probably did something wrong, because you should be getting values that show up on the table. So you shouldn't be getting any values that are too far from values that are on the table. So 4,700 minus 3,500, then divide by 550, and you get 2.18. So now we're doing this problem. What's the probability that z is between negative 1.09 and 2.18? So to do this, we calculate the larger, then we subtract the smaller, and 2.18 on the table, we're going back to where we just read the table normally. 2.18 is over here at 0.9854. And then negative 1.09 is here at 0.1379. We do that subtraction, and our final answer is 0.8475. So what does that mean? Well, here we would expect about 84.75% of babies to be between 2,900 and 4,700 grams. Now, the next question, what's the probability that a randomly chosen baby will have a birth weight greater than 4,500? So what we're doing here is we're finding the probability that x is greater than 4,500. Let's make this into a z. And we take 4,500, subtract the mean of 3,500, divide by the standard deviation. This gives us 1.82. It's a greater than problem, so we have to do 1 minus the probability that z is less than 1.82. So we need to look this up in the table, 1.82, and that is this 0.9656. Do our subtraction, and our answer here is 0.0344. So that tells us only about 3.44% of babies are greater than 4,500 grams. We can answer the question, what weights represent the top 10% of birth weights? So we're looking at the top 10%, but remember the table doesn't like the top percents, it wants the bottom percents. So on the table, we want to look at the bottom 90%, so 0.9 in the table. So we go over to our table and we're looking for 0.9, and it's usually like hunting for Waldo. All right, 0.8997 is the closest that we can get to 0.9, and that corresponds to 1.28. So here's what's challenging about this particular question. We just figured out the z value, but that's not relevant to this problem. 1.28 doesn't mean anything in the context of this problem. We want to know the weight, but remember, the weight was found by taking a value, subtracting the mean, which in this case is 3,500, and dividing by the standard deviation. So we can actually solve this equation and get the value for x. So just a reminder of solving these types of equations, you cross multiply. So you have 1.28 times that denominator, 550. So you're looking at 704 equals x minus 3,500. And then the next step, you add 3,500. And we're looking at 4,204. These are in grams. So the top 10% of babies weigh 4,204 grams or more. These questions will always follow that same procedure, multiply by the denominator and then add the mean. We can also look at the middle 95%. So remember the middle 95% was looking at the bottom 2.5% and the top 2.5%. So we could look this up in the table, but we already did this one. We found that it was negative 1.96 and positive 1.96. So we do need to get both of these values to section off the middle 95%. So we'll start with a negative 1.96, and we're going to solve this. So we cross multiply, negative 1.96 times 550. We get negative 1,078. And then we add 3,500. And we're looking at the bottom of this range being 2,422. And then we'll do the top 1.96. Now this time it won't have that same symmetry because we're not centered around 0 anymore, so you can't take any shortcuts here. You actually have to do it. Positive 1.96 times 550. You are looking at, the same number when you multiply, just positive and negative, but when you start adding and subtracting, you don't get that kind of symmetry. So when we add 3,500 to that number, we get 4,578. So values between 2,422 grams to 4,578 grams represent the middle 95% of birth weights.